In the last video we built this Sallen-Key filter, which is a nice two-pole filter and it works quite fine, but it is one thing that I don't like, is that the high-pass filter is completely different than the low-pass filter, which gives the filter a character. So this is definitely something that you can use and it sounds good, but I would like it better if it would be the same character as the low-pass. Because of that's what will make it usable for, let's say, EQs, and will make the filter equivalent to let's say a biquad but stable. So this is going to be the state variable filter, which we call SVF, and the topology of the state variable filter is like this, that we have one integrator and with an input of X and the output of Y. And just to remember that inside the integrator we only have a multiplication and an integration, and the integration is going to be the trapezoidal integration, so it will look like this. If you want to know a bit more, then look up my earlier video or just take a look at the or read after it, let's say in the virtual analog filter design book by Vadim Zavaleshin. And yeah, here we will multiply instead of G by half omega. And yeah, to not confuse anyone with the numbers and letterings, I'm gonna just quote this W from this part on. And we half omega is fine because of we do not have the additional feedback loop where we subtracted the S from the input. So that's why half omega is fine, because of we do not need to correct it for the feedback. And yeah, this is going to be the S output here, but that doesn't matter, just take a look at the structure now. So we will have two integrators, one will go into the other, and this is going to be the low pass output, and this is going to be the input of the filter, and from the input we are going to subtract, and we will have a feedback loop which adds the two integrators together and sends it back to the feedback. And resonance will be the scaling of the first integrator, so we will just multiply it by the value of the resonance, and W is just going to be the cutoff. So these are our parameters, and indeed we can start to write up the equations for these, so we can calculate the feedback. But just like by the Sallen-Key filter, we won't calculate the low pass output, but we are going to calculate the whole pass that goes in here, so which is this value. So basically we need the additions output for Y, so we are going to call this part Y here, let's say like that. So let's write up the equation for the state variable filter. One more thing that I have to mention is that the formula for the integrator is going to be the same, like we had X times G plus S for the one-pole filter, and these won't change. We're just going to multiply by W because of these weightings are fine. With G we calculate it with the scaling of half omega, but here we don't have it, we just have the equation X times W times plus S, and you can see that indeed that's what inside here. So this is fine, and the input of the first integrator is simply X minus Y, and this should be fine. And then we have integrator 2, which is just I1 integrator 1 times W plus there's no S here because of S is the history of the first trapezoidal integrator. So if I call this S, that would be misleading. I just call it Q, but that's the same logic behind it. And then we can write up ITU like, instead of I1 we can use the formula for I1. So we do not need any additional variables. And then we can write up Y, because of Y equals I1 times K plus ITU. And we have the equation for I1, simply replace it. Then we have the equation for I2, simply replace it. And we can go into Wolfram Alpha with this, which I won't do now because of I did it already, and I can write it up like it's going to be this formula divided by, and we can go into the previous filter structure and just do whatever we have to do. So first thing is that this is going to be a subtraction here. Then inside the one-pole filter we have to remove these. And this is going to be S, and we don't need this part here, and we don't need this subtraction. So we just have the X input times X plus S that we have, and the trickery to have everything in order and only have one Z. So this is fine. Let's call this I1, and let's go into I2, change it from the one-pole filter to strip it down to the integrator. So we remove the feedback, we remove this here, and Q is just this output here. And actually this should be fine like this. Yeah, let's call this W, underline W, same thing here, W, underline W, and yeah, let's erase this here, and yeah, let's make it from scratch. So we need the input of X, we need the, oh, this is still the Sallen-Key equation here, sorry. So we need X, we need W, we need S, we need Q, and we need K. And W is the only thing that we need to square. Like this. And we just need to create all this. So multiply W squared by X, that's going to be V1. Then multiply G with K. So no, not G, this shouldn't be G, I wrote it wrong. So this should be W, K, and X, sorry. And this should be WS, this should be the other, it's all the rest is fine. I was just copying from the wrong formula. So WKX, WK, which is this, multiplied by S. Then WS, like that, and KS, and Q. So we should be fine like this. 1, 2, 3, 4, 5. Yeah, we are right. And let's do the denominator, which is going to be W times W and K. Oh, here it's this is an add. And here we add 1 to it. And this is our denominator. Nice. And actually this should work from this point on, because everything is right except that I didn't connect this. So X goes there, Y is not required for the numerator. Nice. So this should actually work. We just need to plug in the half omega into the input. Let's call this half omega once again. Nice. So let's cut this patch, paste it back and hope that it's going to work. And something's wrong. And I don't know what. Let's take a look at what we have here. W and K. That's fine. Oh, this shouldn't be S, this should be X. Oh yes, it looks fine. Oh yes, it is. Sorry. Okay, I will fix this inside the box as well. So all we need to do here is to, instead of S, we need X. Like this. Oh yes, and now we have a proper working state variable filter. Let me clean up the patch a bit. So we have the equation for the state variable. We do not need that. We do not need this here. And all we need to do is to find the pickup points for the filter to have all the to make it really multi-mode. So here we have the high pass. So X here is basically the high pass output. And this output here is the band pass. So I create that first. So we have the order. Indeed, it's the band pass and it works fine. With any resonance, we can go really high. Then it will be very steep. And at 2 we have the 1-pole filter feedback or the 2-pole filter, the resonanceless. Okay, then this is the high pass output. Let's take a look at it. And this is very, very fine. And if you look at the low pass, they are symmetrical. So now we do not have that asymmetry. They have the same resonance, they have the same slope, and they add together fine with the band pass. So you can use this for EQs, like just add them together. And you have a little peak there, but that's because of the resonance is not on 1. So now you have the simple state variable filter, like in an EQ configuration, like you can create shelving with this much. And you can have fun with it. Let's create some additional outputs. So the notch output is just the low pass plus the high pass. Nice. And you can have the normalized bandpass, which is just the bandpass output multiplied by the resonance. And that's a very useful output as well, or pickup, because of, if you look at it, its peak is always at 0 decibels. So whatever you do with the resonance, the peak stays at 0 decibels, which is extremely useful if you want to build EQs. So this is why, for me, why the state variable is superior to the Sallen-Key filter, because of the possibilities it gives to you in terms of flexibility and in terms of these pickups that work so nicely, which the Sallen-Key doesn't have. Sonic-wise, they are completely the same, so except the high-pass filter, which is a lot harsher by the Sallen-Key, but the low-pass and the band-pass are completely the same in both filters. So they are just two-pole filters, and they do what they have to do, but this is very flexible. So I use state variables all the time. So that's it for today. You can download this patch from our Discord, and you can play around with it and see what you can come up with. I think that this is all that I can tell you about filters. You can go more complicated and look for topologies that you are interested in, and we may try to build them if you want to. I'm not encouraging anyone, because I still think it's kind of a waste of time, because there's enough filters out there, and there's not that much sonical difference in between filters than people think there is. They have different feels, but at the end of the day, they can get pretty close, and I don't think that using specific filters will make your music a lot better. I think if you need a two-pole design, then one two-pole design is enough. If you need a four-pole, so a steeper one, then any ladder filter will do basically the job. Except if you are going for emulation of typical analog equipment, then things will get a bit more hard, a lot more hard to do, and I'm not sure if it really makes your music a lot better, or your sounds a lot better to use analog emulations, but that's a question of taste. This is just my point of view. So I hope you found this interesting, and I hope these videos made sense. From my point of view, this topic is now closed. I did everything I was able to show. Probably I could also build a four-pole Moog, but that's after these two filters, that's just the same procedure, so I don't think it's necessary. But you can grab this patch from our Discord and have some fun with it, or yeah, study it, or whatever you want to. And thanks for watching. Bye bye.